Projectiles inclined plane, type 3, horizontal landing. So this is our second example, which is from your textbook, page 184. And we're looking at the worked example, which is 10.3. So here we have a particle projected up an inclined plane and with an initial speed of u. The line of projection makes an angle alpha with the plane as opposed to with the horizontal, and then the plane itself makes an angle of beta with the horizontal. And we have to prove that when the particle lands horizontally, then we have tan alpha, tan squared beta is equal to tan beta minus tan alpha. So that's the first part of the question. And then the second part is, given that beta is equal to 45, find the value of tan alpha. Now again, students often look at these questions and go, oh my god, how am I going to find this statement? And again, it's not about how do you find the statement, it's about what is the information given to you in the question and how do we go about these questions normally. Now don't ever worry about the proof bits until we get to the end. So we have our inclined plane. And what do we know about the inclined plane? Well, it's making an angle beta with the horizontal. We have a particle that is projected up into the air. And it's projected up into the air with an initial velocity of u meters per second. Now, when its trajectory is going through the air, it lands so that it is horizontal to the ground. Now, we know that if we have two parallel lines and a transversal cutting it, that these angles will be equal. So there's our landing angle, and we have alpha is the angle of projection. So therefore, if we have a horizontal line and a parallel line and two parallel lines and a transversal cutting it, that beta must be equal to L. So again, our landing angle will also be the same as the angle of the inclined plane. So again, key to our question here. Now we also know that on landing, Sy is equal to 0. So that will always help us find our time of flight. So what you're going to do for me is you're going to make out your table for U, A, V, S and T in both the X and the Y direction. So you're going to pause the video and complete the table. So if we've completed the table, we know that U cos alpha, we know that our U is equal to U cos alpha I and U sin alpha J. So filling out our table, we have U cos alpha in the X direction, U sin alpha in the Y direction. And we saw in the last example, example 1, that when we resolve our gravity, when we're going up an inclined plane, we end up with minus G sin beta in X direction and minus G cos beta in the Y direction. So it's always handy to spot that it's cos alpha, sin beta, sin alpha, cos beta. And they're both minus when we're going up the inclined plane for gravity. So then subbing into V equals U plus AT and subbing into S equals UT plus a half AT squared, we end up with our 4 equations for Vx, Vy, Sx and Sy. Okay, so what are we going to do? Well, the key to the question, as we said at the start, is the fact that it's landing horizontally, and therefore we have two pieces of information, which is our Sy equals 0 and our landing angle is equal to beta. So let's start like we always do by saying on landing, what do we know? Well, we know that Sy equals 0, and we saw in our table that Sy is equal to U sin alpha t minus a half G cos beta t squared. So therefore, if I left that equal to 0, then I multiply across by 2. I'll be able to take out the highest common factor, which is of course t, leaving me with 2u sin alpha minus g cos beta t. Now if both factors multiply to give us 0, that means that one of them must be 0 or both of them must be 0, which leaves me with 2u sin alpha minus g cos beta t. And if I rearrange to get t on its own, I get 2u sin alpha over g cos beta. So this is my time of flight, because the only two times that the displacement above the ground is 0 is at the start and at the end. Okay, so my next piece of information is that I know the landing angle is equal to 0. Or not 0, sorry, equal to beta. Because it's landing horizontally. So what do we know about our landing angle? Well, we know that tan L is equal to minus Vy over Vx. So this time I'm going to show you what it would look like if, rather than getting the two times and equating them, I take the time of flight that I've worked out and I sub it into the Vy and the Vx and then try and get out what it is I'm trying to prove. It doesn't make a difference which way you do it, as I said in the last video, but sometimes people prefer one way or the other. So in this example, we're going to use the time of flight that we've just found, which is 2u sine alpha over g cos beta. Okay, so this will be, this will be our landing angle at the time of flight. Okay, so we can work it out all in one go, or we can work it out separately. So because I'm going to be subbing in the time of flight, I'm actually going to work out Vy and Vx separately and then sub in into the equation, just because otherwise it can get a bit messy. So we know that Vy from our table is equal to u sine alpha minus g cos beta t. So I'm going to sub in my time of flight there. So we have u sine alpha minus g cos beta, and that's by the time of flight, which is 2u sine alpha over g cos beta. And that's nice because my g cos betas are going to cancel, which leaves me with u sine alpha minus 2u sine alpha, and of course then that gives me minus u sine alpha. Okay, so now I have my velocity in the y direction. Well, let's do the velocity in the x direction. So my velocity in the x direction was u cos alpha minus g sine beta t. So again, if I sub in my time of flight, well, my time of flight is 2u sine alpha over g cos beta. So this time we don't get any cancellation except for my gravity. But what you should notice is that you have a sine beta over a cos beta there. And we know that sine over cos is equal to tan. Okay, so we have u cos alpha minus 2u sine beta over cos beta is tan beta, and then I'm left with a sine alpha. Okay, so we're getting one tan out here now. So now we have v in the x direction and we have v in the y direction. So now I'm going to put that all into my landing angle formula. So we know that the landing angle, of course, is also beta. So rather than L, we're now going to say beta for the landing angle is equal to minus Vy. So that's going to be minus u sine alpha, which is going to become plus u sine alpha. And that's all over v of x. Well, v of x is u cos alpha minus 2u tan beta sine alpha. Okay, so what are we going to do? Well, we're going to cross multiply. And if I cross multiply, I'm going to end up with tan beta multiplied by u cos alpha minus 2u tan beta sine alpha is equal to u sine alpha. And I can see u is common there, so I'm going to take out the u, and then I'll multiply with my brackets. So I have tan beta times cos alpha have tan beta by tan beta. And a 2. So tan beta by tan beta is going to be tan squared beta. Sine alpha is equal to u sine alpha. So now my u's are gone. So it is only now at this point that I'll go, okay, but where am I trying to go? So everything up until this point has just been landing angle, subbing it into the formula, and s of y is equal to 0 in time of flight. So now I'm seeing that I'm left with a whole load of tans and coses and sines. So now I'm interested in what was the statement I'm trying to prove, and I go back and I see that it's 2 tan alpha, tan squared beta is equal to tan beta, tan alpha. So this is what I'm trying to get out here. Okay, so that basically means I need to get rid of all of my sines and coses and only have tans left. So how am I going to do that? Well, I can see I have the tan squared beta and I have another tan beta here. So what am I missing? Well, I'm missing the cos, or the tan alpha, I should say, sorry. So what I'm going to do is I want to try and get rid of everything here, and I need to get rid of these sines and the coses. So I could divide across by sine, or I could divide across by cos. That's up to us what we want to do. But I know that if I go back to the original statement, that my tan squared beta is multiplied by tan alpha times 2. Now if I look here, I have the tan squared beta and I have the 2, so I need this one here to become tan alpha. Now the only way I can get tan alpha is, of course, if I divide across by cos alpha, because I know that tan is equal to sine over cos, no matter what that angle is. Okay? So let's divide everything across by cos alpha. So that gives me tan beta cos alpha all over cos alpha minus 2 tan squared beta sine alpha all over cos alpha is equal to sine alpha over cos alpha. And now we're pretty much done, because my cos's are gone and my sine over my cos is going to become a tan. So therefore I have tan beta minus 2 tan squared beta tan alpha is equal to tan alpha. And then if I rearrange it just to make it look the way they've given it to me, my tan squared beta must be on the left hand side, and I'm going to multiply across everything by minus 1. So therefore that gives me 2 tan squared beta tan alpha is equal to tan beta minus tan alpha. Done. Lovely. Okay. So what you're going to do for me then is I'm going to give you the exam questions attached separately, and I'll mark 2 of those exam questions for you then, okay? So that'll be in the post just above the videos. So if we go back to the second part of the question, it says find tan alpha if beta is equal to 45 degrees. So if beta is equal to 45 degrees, we're clearly going to start off with the statement, because we've just proved that that statement is true. So in other words, if beta is equal to 45 degrees, then we have 2 tan alpha tan squared beta is equal to tan beta minus tan alpha. So we have 2 times tan alpha, tan beta squared, well that's tan 45 to b squared, so always be careful with trig. Tan squared is tan of the angle to be squared, and then tan beta, so again tan 45 minus tan alpha, and we love tan 45 because of course that is 1, which leaves me with then 2 tan alpha is equal to 1 minus tan alpha, and therefore we have 3 tan alpha equals 1 and therefore tan alpha equals a third. So it doesn't say find alpha, it says find tan alpha. So therefore that is the end of the question.